Okay, so I'm going to talk about my recent work on the quantization of special Kähler manifolds. I'm trying to understand how to switch back and forth, but I guess I didn't get it. Yeah, I'm trying. Okay. Thank you. So I'll start. This is a very old topic. I'll start by reminding where special Kähler manifolds arise in the physics literature. So physical origins of special Kähler geometry. Affine special Kähler manifolds arise as vector multiplet moduli spaces in n equal to rigid four-dimensional supersymmetric gauge theory. And projective special Kähler manifolds arise in the corresponding n equal to supergravity theory coupled to scalars. From the point of view of string theory, projective special Kähler manifolds arise as moduli spaces, we'll call this M throughout, of twists of n equal to 2, sigma models on 3 Calabi-Yau manifolds. So the main object of study in these theories is the generating function of all scattering amplitudes in a theory labeled by a point P in the moduli space. And the scattering is among marginal fields, so roughly half of the marginal fields, these that survive the twists. And these are labeled by U here. And these Fi1, In, G are scattering surfaces of genus G with insertions of these marginal operators. Now, it was shown long ago in 93 that Z satisfies a master equation, or it's actually a set of differential equations collectively called the holomorphic anomaly equation. So the aim of the talk is twofold. First of all, I will give a new origin. Well, it's not. I'll explain how special Kähler geometry arises from the structure of quantization. So you don't have to feed it in, but it arises from the structure of quantization. In particular, affine arises as, in some sense that I will explain, as the simplest quantizable geometry, and affine conic as the simplest quantizable geometry plus a Hamiltonian, which I will explain. The second aim is to quantize the special Kähler manifolds in general, recover generalizations of the holomorphic anomaly equations, and their general solution, or the kernel to the holomorphic anomaly equation. So the main input for this study are the famous work, so they're old works of 20 years ago. The first one by Witten on background independence in string theory, where he was shown for the first time, or there was the idea already there that somehow the quantization of the moduli space had to do with a higher genus expansion. Of course, this is one of the main points in string theory in general. Has to do with the framework of quantum gravity in string theory that has to do with higher genus expansion has something to do with quantization of gravity, but one has to show it. And in this case, let's say we show this in a very simple case, that quantization and higher genus expansion are really the same thing. And the other paper that came out essentially the same year was a paper by Fedosov on quantization on symplectic manifolds. So putting those two things together essentially gives you the desired result. And some developments which corrected some of the work in Witten were already in 2004 by Verlinde. So let's start with a definition of quantization. This definition, there are many definitions. From the point of view of deformation quantization, a la Kontsevich, a symplectic manifold is trivial locally. But of course, from the real point of view of quantization, so the problem is trivial. From the real point of quantization, the problem is not trivial, and as we will see, the Riemannian structure of the manifold plays a fundamental role. In particular, it may distinguish between negative norm states from positive norm states. So let's start with the definition that the quantization of a phase space M is a map from M into an infinite projective space. We can view this as the classifying space of smooth line bundles over M, and we put a structure here which is like the transition probability in quantum mechanics. And so this is the quotient of a separable Hilbert space by C star. And so the problem of quantization is the classification of this pair, phi and m. And m is comes with no structure rather than that of a smooth manifold. All this geometrical structure, so this is the philosophy of quantization, arises by pulling back via phi from P infinity. So complementary to this classification is the transport to m via phi of the basic invariance of P infinity with this pairing, in particular the group of automorphism of P infinity, the Lie algebra, which we know as the physical observables, and the universal enveloping algebra, some suitable completion thereof, which is known as the algebra of observables. In particular, if we denote by P a representative in the sphere of what's called a coherent state, phi of P, corresponding to a classical state P, namely a point in the classical phase space, then one recovers classical observables as expectation values of the quantum observable in the coherent state P. And the star product is defined via this relation, and so it should represent the product of quantum observables. The problem in finding star products is that of somehow being able to sandwich here something that allows to split PFP and PGP. So it's a very simple exercise in quantum mechanics to do this for canonical quantization. So let's look at canonical quantization. We review a little bit and then we go to the case of interest. In canonical quantization, m is equal to Rn, and we want to look at the maps from Rn into P infinity. Of course, there is a huge number of maps from Rn into P infinity. What we mean by canonical quantization is we really presuppose that Rn is not a smooth manifold, but it's a vector space, or better, it's the orbit of the group of translation acted on the origin. And then the maps of interest are induced by projective representations of this group gamma. And these are in one-to-one correspondence with central extensions of gamma. And the central extensions are exactly constant Poisson structures on gamma. We will restrict ourselves to the case, to the symplectic case, which somehow correspond to injective maps. And in that case, we still have to fix the image of the origin 0. So, and for this, we just fix the ground state of a harmonic oscillator Hamiltonian, or if you want the highest weight state of the representation of the Heisenberg algebra, and this highest weight is defined by a choice of complex structure on Rn. Okay, so Fedosov's approach to quantize a general manifold M works as follows. So fix a point P0 in M, and let's map this to phi of P0. Then an arbitrary point P is mapped to phi of P, but phi of P, I can always write it as, say, a matrix which depends on P and P0, or an operator times phi of P0. Now, since this only depends on the endpoints, I can view this as the path order exponential of a flat connection on a trivial Hilbert bundle on M. And I can also view it as a trivial projective bundle, but then also as a Hilbert bundle. So we have traded the notion of map phi from M to P infinity with the notion of a flat connection on a trivial Hilbert bundle A, so it satisfies dA plus A with J is equal to 0. And we still need the choice of the image of a marked point, P0. So now, this is all pretty trivial. The nice thing when we have a symplectic manifold is that there is a nice classification of the solutions to this equation. So if we want to classify all possible geometries we can get via this procedure, we can do this in the case of a symplectic manifold, and this is Fedosov's approach. And this works as follows. So if we have a symplectic manifold, we restrict attention to a patch, and we can cover the manifold with coordinates, so patches where the symplectic form is constant. This is Darboux theorem. Accordingly, we will have a Heisenberg algebra, and with respect to this Heisenberg algebra, we can write an expansion for A, as polynomials in the Heisenberg algebra. And this is well defined in a suitable topology. And now each of those coefficients depends on the classical phase space and will give the geometry on the phase space. So in particular for canonical quantization, the corresponding A stops at first order in the x-axis, and by plugging this A into the Marer-Cartan equation, we find that d alpha is equal to -1/2 omega. Okay, so now let's stop at second order. So at second order, we'll leave the first order as in the canonical case, and we add this piece, and we can assume without the loss of generality that A is actually anti-Hermitian. And what if we plug this into the Marer-Cartan equation, the A plus A with J is equal to 0, we find these equations. Again, the alpha is equal to -1/2 omega. And then we have this object G, which is related to D. And this is actually, one can check that this is actually a connection on the pullback of the tautological line bundle from H to P infinity back to M, while G is a connection on the tangent bundle to M. And this says that it's symplectic, it's torsion-free, and it's flat. So we will have to think of this as the Gauss-Manin connection. Now, actually, first order and second order A's are the same. And in fact, there is a coordinate transformation sigma, symplectic coordinate transformation, and corresponding gauge transformation in the Hilbert bundle that such that G vanishes and maps an arbitrary Darboux coordinate system to what's called a special Darboux coordinate system. So on the special Darboux coordinate system, this symplectic flat connection on the tangent bundle vanishes. Now, how do we recover special geometry? Well, special geometry is just corresponds to first order connections which are compatible with the choice of an almost complex structure on M. And by compatible, it means that A induces a holomorphic map from M into P infinity. So A always, by choosing an almost complex structure, I can split A by a holomorphic part and an anti-holomorphic part. And the compatibility is that B alone is projectively flat and therefore induces a holomorphic map into P infinity. So again, checking the flatness condition, so dB plus B wedge B is central. We find a constraint on, we find that J is integrable, and we find that the Kähler metric, Gij, is the Hessian of a function, K, and this is the special Kähler potential, K of special geometry, and we recover exactly the structure of a fine special Kähler manifold. Okay, so now that we have recovered the structure, we can proceed to find wave functions. And what we want to do, well, P, the state P really depends on the choice of gauge for A. And I don't allow for any possible gauge transformations, but just the ones that correspond to coordinate changes. And I would like to encode this state P as a symmetric covariant tensor on the phase space M. And so I will choose a basis or an overcomplete basis of states U yet to be defined, where U labels an element of the tangent space at P. And so what should I choose for this state U? Well, it's an element of a tangent space of a vector space, and the natural choice is just the coherent state that corresponds to the element of the tangent space, so canonical quantization of TPM. Like this, ZA is not exactly a tensor. It will be a section of symmetric tensor twisted by a line bundle. Now, this line bundle is made out of two line bundles. This is the pullback of the tautological line bundle via the quantization map. While this is a line bundle yet to be defined, and the reason why I can expect the introduction of a further line bundle is that these states U are always defined up to a phase. And we will fix this later on. So this in particular will have curvature -1/2, the symplectic form. And one can check that the states U are parallel transported by the lift to the Hilbert bundle of any symplectic compatible and metric compatible connection, in particular the Levi-Civita connection gamma. Now the master equation is simply the statement for Z, is simply the statement that P is parallel transported by the connection A, written as a differential equation for Z. And the integrability condition fixes the line bundle L prime, and in particular, one introduces a natural connection beta on this line bundle, and the curvature of this line bundle is exactly, so mu nu bar, this is the only part of the curvature which is non-vanishing, is the Ricci tensor minus the metric. So this might have something to do with higher spin theory, but that's something that has, at least from a physical interpretation, nothing clearly to do with this case of topological strings. So we can twist this trivially to an anti-holomorphic line bundle. In particular, the tensor C that represents Z becomes, we'll call it a tensor S, and we'll find that the master equation for S is these two equations. This will give recursion relations for the various homogeneous terms in this tensor S, while this reduces to an equation for a single section of the line bundle on M. Okay. So now, in order to construct the kernel of this differential equation, we choose an overcomplete basis Y of coherent states of the tangent space at P0, and in special coordinates, so when A is first order, if I translate P0 to P, I'll find that this state will just go to the same kind of state, but translated by the coordinates of P in terms of P0 in special coordinates. And by this construction, one can find the kernel of the holomorphic anomaly equation. So if I have a solution at P0, I can transport this everywhere. So now we go to conic special Kähler manifolds. A conic special Kähler manifold is an affine special Kähler manifold with a holomorphic vector field H, such that the Gauss-Manning connection of H is the projector onto the holomorphic part of the tangent bundle. So this kind of equation is always true for affine special Kähler manifolds. Here the constraint is that H is holomorphic. Equivalently, one can write that K is homogeneous of degree 2, and now we ask where does this property arise from the point of view of quantization? And so the possible origin from quantization is the following. So assume there is an observable, a quantum observable K that preserves the space of coherent states. Then the corresponding classical observables is exactly homogeneous of degree 2. So all the so this puts constraints on the choice of P. So and so this constrains down the solutions to the holomorphic anomaly equation. And chi here is just the Hamiltonian flow with Hamiltonian K. Now we move to negative signature. So we're interested in Lorentzian special Kähler manifolds. And there is an obvious problem. So if I have a negative metric, let's look at the simple case of R2. If usually I have the Kähler structure omega g j, but now I go to minus omega minus g minus j, and we choose the highest weight representation just as in the positive case covariantly, we have an obvious problem. This representation is not unitary, meaning there is no positive definite Hermitian bilinear form with respect to which the generator of the Heisenberg algebra are Hermitian. So this introduces Gauss and so on and so forth. So one way to deal with this is to introduce instead two bilinear forms. One is positive definite, so that it gives a topology to the representation. The other one instead is indefinite, and one can view it as B plus composed with -1 times a fermion operator. So this fermion operator exchanges an odd number of modes with even number of modes of the generators of the Heisenberg algebra. And now the important thing is that this connection A is not an isometry with respect to B plus anymore, it's an isometry with respect to B minus. And this introduces a problem, in particular as a Hilbert bundle this is non-trivial anymore, but the important thing is for topological reasons and convergence is that one can still trivialize it on open sets, and therefore the whole discussion still works. So now let's go to general Lorentzian special Kähler manifolds, and we consider just the portion of the Lorentzian special Kähler manifold where the special Kähler potential is negative. Then the positive directions are exactly the orthogonal complement of the Hamiltonian vector field of K and the Hamiltonian vector field of K multiplied by the complex structure. And these are this is the projection onto the positive part of the tangent bundle, which we'll call horizontal bundle. And the normalization conditions on the state P changes. So we have this PU minus 1 minus P and this extra factor. So this normalization condition is important because then it allows us to write a general solution by just applying the kernel of the master equation to a solution at a particular point, marked point P0. So in particular, the master equation in the Lorentzian case remains unchanged. Everything is covariant, and the kernel of the master equation, which I'm not writing down here, is one can compute it similarly. So now the quantization of projective special Kähler manifolds n lambda, where h there are coordinates z on the manifold M and coordinates y on the holomorphic quotient by the holomorphic vector field H, which one can write as lambda del lambda. And this holomorphic quotient and lambda, its quantization is defined by the reduced wave function z reduced, which is now not just up, but involves a projector onto the horizontal bundle and the map from n lambda onto M. And n lambda comes endowed with a natural metric, and this metric is the metric on the horizontal bundle, which is also the Marsden-Weisstein quotient of the metric on M. And the symplectic, so we have holomorphic quotients and a symplectic quotient both playing a role. They're not exactly the same. And the various symplectic quotients differ only by a scaling factor. And so we can identify the scaling factor with the notion of Planck's constant, or minus Planck's constant, inverse Planck's constant. And finally, we get the generalization of the holomorphic anomaly equation for an arbitrary projective special Kähler manifold. And in particular, we also get this equation here, which tells us that the counting parameter of the various higher genus Riemann surfaces is anti-holomorphic. And so, in conclusion, we've seen how special Kähler manifolds arise as the simplest generalization of canonical quantization in the framework of Fedosov's quantization of symplectic manifolds. We've given a possible origin of conic affine special Kähler manifolds. This restricts the choice of coherent states P. And we obtain the correct generalization of the holomorphic anomaly equations and their general solution. And now, of course, there are various important, various interesting questions one can ask, and in particular, what happens if I increase the order in Fedosov's expansion? And this might have something to do with decreasing the amount of supersymmetry in 4 dimensions. And this is something that one can further look at in the future. Okay.
Any questions for Michael?